Hi, my name is John Slattery, and I'm the lead of the Argonia Cup competition team for FFAero here at Kansas State University. Having competed at Argonia Cup for the last 2 years, FFAero is excited to be returning to Argonia. This year, we are proud to introduce a new vehicle known as Dragonfly. There are 3 main components in this year's entry. We have the rocket body and the propulsion system, the tracking system, and finally, the remote-controlled plane that will guide the payload back to the ground.
Hi, my name is Herbic, and I'm a member of the Booster Sub-Team. This year, as always, we model our rocket in OpenRocket and SolidWorks, and we 3D print and laser cut a lot of the components. This year, we'll be flying an L1090, a non-sparky motor with a reusable casing. And to retain this motor, we're going to use a 54mm blue tube with 3 wooden centering rings.
Hi, I'm Parker Lange, another Booster Sub-Team member. In FFAero, we custom build all body tubes using 9-ounce E-type fiberglass.
As you can see, the fiberglass is rolled over a PVC mandrel with a layer of wax paper. Epoxy is poured over the surface and spread with a chip brush. Once all layers are wrapped, the tube is set to dry. For this vehicle, we have 3.7-inch tubes. The nose cone is wrapped in a similar way, except this is done with carbon fiber thread over a 3D printed mandrel.
My name is Madeline Bermond, and I am a member of the electronics sub-team. Due to the addition of a controlled payload vehicle to the rocket this year, the team decided to develop an automated tracking system. This tracking system uses GPS data sent from the plane to a 915 MHz antenna. The data is then processed and used to move the antenna so it can follow the glider as it flies. A second antenna is used to receive a live video feed from the glider to help with flight. To control this, the team developed a system we call SpacePi.
I'm Brian Parks, another electronics member. SpacePi contains modules and specific drivers that are used to control the ground station. It also includes a networking aspect to be able to communicate with multiple antennas and other subsystems. To manage this, a user interface was developed to watch all messages on the network. That way the team can see what is going on. This system was also written in a way such that it can be expanded and reused from year to year so that team members can grow and explore further aspects.
I'm Blaine. I'm Brett.
I'm Zane.
And I'm Cade.
And we're the RC Plane Sub-Team.
With the constraint of the vehicle having to fit inside the small diameter of the rocket, a lot of standard RC designs and proportions wouldn't really work. To combat this, the wings are spring-loaded with wire connections down the middle of the fuselage, kind of like a crossbow. They also have a parafoil design and were sewn in-house using ripstop nylon.
The tail has a cruciform shape in order to align the horizontal and vertical stabilizers along the diameter of the tube. The elevator is controlled by a system of servo to pushrod to control horn. As many control rods are less than 3 inches long, we had to design in a guide system, as our pushrod is over 1 foot long.
The electronics allows us to have control from up to 5 miles away and video feed from a line of sight. The propeller blades fold back to save space in our rocket when stowed, and our power unit results in a thrust ratio weight greater than 1. This should allow us to pilot the glider into the wind and reach our target safely. Analysis has proven this on Excel and confirmed that our stability of the plane should remain adequate.
All in all, the vehicle is simulated to reach just over 8,400 feet with a maximum velocity of 302 meters per second. This assumes a launch angle of 7 degrees from vertical.
Hi, I'm Schmoll, president of FFAero. Now, if there's anything that we've learned the past couple of years at Argonia, it's that unforeseen circumstances such as strong winds or electronics damage upon landing or additional testing could result in our disqualification. Because of this, we've prepared a backup plan. If needed, this capsule will house the golf ball payload, an Ultra Spectrum Easy Mini, a 9-volt battery, a chute, and a black powder charge. With this, the upper portion of the rocket body can be shortened, resulting in less surface drag and thus a higher apogee. The capsule will eject from the rocket with the drogue parachute. It will then fall to around 1,000 feet, at which point the enclosed parachute will be triggered.
On behalf of the entire Argonia team, we'd like to thank our sponsors and donors for supporting this project, and we'd like to thank you for your interest in Project Dragonfly. We'll see you at the Argonia Cup.